Hello, everyone. So today we're going to go on to chapter 13, binomial distribution. So this is going to be part of the probability and distribution, the theory part of the course. So before we start, we're going to go over the symbols again. So make sure you are familiar with all the symbols. N, small n, sample size. Big N, population size. Sigma, population standard deviation. S, sample standard deviation. Mu, population mean. X bar, sample mean. Z, standard normal variable. We're going to learn normal distribution next chapter. R, correlation between two numerical variables, B1 and B0. They're regression coefficients. So B1 is a regression slope. B0 is regression intercept. And p-value and alpha, they're both using the hypothesis test. P-value is the probability of observing a sample as extreme or more extreme than the sample you collected if you assume the sample is random sampling. And alpha is a type 1 error rate. So we're going to talk more about p-value and alpha in detail when we go to the inferences. All right, so the learning objective. First, we need to be able to identify if we can use binomial distribution to solve some practical problem. So basically, how do I know if a variable has binomial distribution or not? Right? So there's a binomial setting we can use to verify that. And then also, if we realize there's a binomial distribution, then we need to be able to find probabilities regarding to the binomial variable. And then, apply the binomial distribution to practical problems. And then just a note, binomial distribution is a discrete distribution. And the sample space will be from 0, 1, 2, 3 up to n. So we're going to talk about what the binomial variable is. The first animal for attendance check, this is ostrich. Right, so I'm going to start with the example we had last class. So we talked about a die had 6 faces with 1 face colored red, 2 faces colored blue, and 3 faces colored yellow. And each of the 6 faces has the same chance to face up when you roll it. So remember, in one of the practice in that chapter, we have a question. If you roll 2 dice at the same time and define a variable x as number of dice showing the color yellow, and then ask you what's the sample space and what's the probability of each outcome in the sample space. So we are able to find the probability here, right? If you wonder how all these come out, you can refer to the videos or PowerPoints in chapter 10. So the sample space will be 0, 1, or 2 because they only have 2 dice. The maximum number of dice has a yellow color will be 2, with the smallest number of dice has yellow color will be 0, right? And they have 0, 1, 2 as a sample space. And they have probability, for each sample space listed here. So this is a distribution of this variable x. What kind of distribution is this variable x? This is actually an example of a binomial distribution. But how do I know it has a binomial distribution? How do I identify a binomial variable? So we're first going to talk about a binomial setting. So binomial setting, you have 4 binomial settings. So basically, all 4 conditions has to be satisfied so that you can call a variable as a binomial variable. And before you check the binomial setting, the binomial variable has to be a count variable. So if the variable defined as counting number of something, so for example, number of students in the classroom, number of computers that has viruses in the computer lab, or number of days it rains, or number of cars that's past the traffic light, it's counting something. And then if there's a counting variable, and then you need the 4 settings are satisfied, then you can call that variable a binomial variable. So the first setting is there are a fixed number of n observations. So when you count something, you have to know how many individuals are you looking at. For example, when you're counting, number of students come to a class, you have to know how many students are enrolled in the class first, right? You're counting number of computers has viruses in the lab, you need to know how many computers are there in the lab, in total. So fixed number of observations. And then second setting is that n observations need to be independent. So one observation doesn't affect the other. So for example, when you're counting number of students in a classroom, then you need to make sure that any student, whether they come to the classroom or not, is not going to affect the other student. So they're independent. For the computer with viruses, then all the computers in the lab, if one computer has virus or not, it shouldn't affect the other computer. If that's the case, they're independent, right? And then the third condition is each observation will fall into two categories. And for the two category, we define one as success and the other is fail. Okay. And then the last setting is the probability of success. You have a success outcome, right? For every observation. Then for every observation, the probability being success has to be the same. So for example, when you're counting number of computers as viruses, only if the probability of each computer has viruses being the same, then the fourth setting is satisfied, right? So if all four settings are satisfied, you can conclude the variable has a binomial distribution. So now let's go back to the example we have here. So let's check on the binomial settings here. So this is a counting variable for sure because the variable is defined as number of dice, so in yellow colors. So you're counting something, right? So then let's check the binomial setting. The first setting is, do we have fixed number of n observations? And then basically, when you're counting number of dice, so in yellow color, do we know how many dice we're looking at? And of course, we know that we have 2 dice, right? You only roll 2 dice. So the first setting is there. And the second setting, are the n observations independent? So for the 2 dice you roll, are they independent? Well, 1 die, so in whatever color, affect the other die. And if you think about it, it shouldn't affect each other, right? They're individual die. Whatever color shows on the first die, it's not going to affect the color on the second die. So that's checked. So then the third setting is for every observation, you can observe 2 possible outcomes. So for every observation is every die, right? Every die, you need to have 2 possible outcomes. And some of them may say, hey, this is 3 possible outcomes, right? You have red, blue, and yellow. Well, there's a little trick here. For any kind of outcomes, you can always put them into 2 groups. So for example, for the 2 possible outcomes, we can define either yellow or not yellow, right? So you can group, some outcomes together as a group, as an outcome. So yellow or not yellow, that will be the 2 possible outcome. And which one's success? Which one's failure, right? For the 2 possible outcome, we need to define one as success, the other as failure. So which one's success? The success outcome is always the outcomes that are being counted. So in here, you're counting number of yellow dice. That means yellow is success. Right? And then, of course, not yellow will be fail. You have 1 success and 1 fail. So setting number 3 is there. And then setting number 4. For every observation, do we have same probability of success? So for every dice, it has a probability of success. Success is yellow, right? For every dice, what's the probability of getting yellow color? And we can see that we have 3 faces on each die. That's yellow, right? So probability of getting yellow for each dice will be 3 out of 6, right? And if you want to calculate, that's 0.5 or 1/2. So then all four settings are satisfied, we can conclude the variable has a binomial distribution. So variable x has binomial distribution. And the binomial distribution is two parameters, n and p. So n is coming from your setting number 1, n equal to 2. P is coming from your setting number 4, probability of success. P is 3 out of 6. Okay. So then we don't like to write long sentences. We want to use a short notation. So instead of writing the sentence, variable x has a has a binomial distribution with n equal to 2 and p equal to 3, 6, we can just use a notation. Variable x follows binomial distribution where parameter n equal to 2 and parameter p equal to 3 out of 6. So this means exactly the same meaning as the sentence above. Okay, so get used to the short notations. It's gonna help us a little bit on writing. So this is a binomial setting, right? So let's talk about some practices. So for each of the following scenario, we're going to determine if that variable is a binomial variable or not. Okay, so the first one, a university has 2,000 freshmen, of which 60% are males. Randomly select 20 freshmen, and we define variable x is number of males out of the 20 freshmen, right? So is this variable a binomial variable or not? Right, so let's work on this. First, identify the variable. X is number of male students out of the 20 students selected, right? So it's a count variable, then it has a potential. Then we need to check the binomial setting. First setting, do we have fixed number of n observations? So when you're counting number of male students, how many students are we looking at? And we actually have 20 students to look at, right? So n equal to 20. So first setting is there. And second setting, are the n observations independent? So for the 20 students you selected, will one student being male or female affect the other student being male or female? Since this is random selection, right? So it shouldn't affect, they shouldn't affect each other. So this is checked, right? So they are independent. So setting number 3, for every observation, do we have 2 possible outcomes? So for every observation will be every student, right? Can you define 2 possible outcomes out of it? So for every student, we're going to look at their gender. Either they're male or not male, right? So you do have 2 possible outcomes. Then we're going to define one of the outcomes as success and the other as failure. So male will be success. Because what? Why is male success? Because we're counting number of males in a variable, right? So whatever outcome that's being counted is your success outcome, okay? So don't get confused. And then the last setting, for every observation, does it have same probability of being success? So for every observation is every student, right? Does every student have same chance to be success? And we know success is male, right? Right? So we have 60% of males in the whole college, right? And if you randomly select a student, the probability of that student being male will be 60%, and it is the same, right? And we're going through that. All 4 binomial settings are satisfied. So we can conclude the variable x does have a binomial distribution where n equal to from first setting equal to 20 and p equal to from the last setting p equal to 0.6. So for the first binomial variable, we can say binomial n equal to 20 and p equal to 0.6, right? So we verified it using the binomial setting. Right, then the second one, in a college, it's reported 40% of students have lunch at a campus food court. X is number of students having lunch at a campus food court on one day. So now let's look at this. Now we're gonna delete all of this. So number X is number of students have lunch at campus food court one day. Right? So is this variable a binomial variable? Then we need to check with the binomial setting. First, do we have fixed number of observations, right? So when you're counting number of students having lunch at the food court, how many students are we looking at? And we don't have it, right? There is no fixed number of n observations. So then we know this is not a binomial, right? So the variable x is not a binomial. Because of what? Because even the first setting is not satisfied, right? Right, so that's the deal. So next one, a football player has made 80% of his field goal attempt. This season, he attempts 20 field goals, and attempts differ from distance, angle, wind, and other conditions. X is number of field goals he makes this year. So is this variable X a binomial variable? Let's look at it. So X will be number of field goals the player makes this year. So first, identify this as a count variable. So it could have a potential to be binomial. Then we need to check the binomial setting. First setting, do we have fixed number n observations? So when counting number of field goals he makes this year, you know, he's gonna make some field goals, he's gonna miss some, right? Then do we know how many field goals he attempt? And it does give us that, right? This season he attempt 20 field goals. So n equal to 20. So first setting is good. In second setting, are the n observations independent? So will the first field goal he makes or not affect the second field goals he make or not? They may be in different games, right? So one, make it or not, shouldn't affect the other, right? Okay, so independent is good. Second setting is good. And then we go to the third setting. Do every observation give us two possible outcomes? Every observation is every attempt, right? So for every attempt, what are the two possible outcomes? Either he make it or he miss it, right? And which one is success? We need to define one outcome as success and the other outcome as fail. The success outcome is always whatever outcome is being counted, right? So we're counting the field goals being made. So made will be success, right? So this will be success. And of course, the other will be fail. Okay, so we look at the success most of the time. You don't have to worry too much about the fail. Okay, so setting number 3 is good. Then the last setting, do we have same probability of success for every observation? So if you know the football field, when they play the game, if the attempt differ in distance, angle, and wind condition, is it reasonable to assume every attempt has the same probability to be made? It's not, right? If it's closer, it's easier to make, right? When you go against the wind, it's more difficult than when you go with the wind, right? So these conditions will affect the probability of success. So this condition is not met, right? So as long as one binomial setting is not met, we're going to conclude the variable is not binomial. All four of them has to be met to consider the variable as a binomial variable. So this is because setting number 4 is not met. All right, so last one. It's very similar scenario with the one before, but this is in basketball field. So a basketball player make 70% free throws in the past, in a career-wise. And this season, he make 80 free throws attempts. And they're always from the free throw line and no other player interfere. So X is number of free throws he makes this year. So X is number of free throws the player makes in this year, right? And this is a common variable. It could have a potential to be binomial, and we need to check the condition. Do we have fixed number of n observations? And when we check it, this player make 80 free throws in a year, right? So setting number 1 is good. We have fixed number of n. Setting number 2, are the n observations independent? So will one free throw he makes being made or miss affect the other free throws? They shouldn't, right? So they are independent. And setting number 3, are every observation giving us 2 possible outcomes? Every observation is every free throw attempt. Then are there 2 possible outcomes in terms of free throw attempt? So we know for every attempt, it will be either made or miss, right? So between the 2 possible outcomes, one need to be a success, the other is fail. Which one success? Again, we're going to look at what is being counted, right? We're counting number of free throws he makes. So the make will be success. And the other outcome will be fail. Okay, so setting number 3 is there. We do have 2 possible outcomes. And setting number 4, do we have same probability of being success? So since all the free throws are coming from exactly the same free throw line, and it's the same distance, and there's no weather condition, and there's no player interfere, basically, they have the same condition. So it's reasonable to assume, the probability of success will be the same, right? He had the same chance to make each of the free throw attempt. And what is that probability if that's the case? If they are the same, what is that probability? Does it provide us? We know that's 70%, right? Career-wise, he's a 70% free throw shooter. So 70% is 0.7. So all 4 settings are satisfied. We can conclude the variable X does have a binomial distribution. And the parameter n equal to 80 from setting number 1, parameter p equal to 0.7 from setting number 4, right? So the variable have a binomial distribution. Okay, so this is how we identify if a variable is a binomial or not, using the binomial setting. All 4 settings have to be satisfied in order to say a variable is binomial. Right, so we know what a binomial variable is now. Then we need to learn how do we find probabilities from binomial distribution. So here's kind of the calculation part. So binomial distribution has a few formulas to work with it. First is this easy calculations. So for any distribution, we can always calculate the population mean and the population standard deviation, right? So population mu will equal to n times p. You know, if you know what n is, you know what the p is, you know, just like this, right? This is n, this p. And just times together, that will be the population mean. And the population standard deviation will be square root of n times p times 1 minus p. And they're very simple, right? So once you know the parameters of the binomial distribution, you can calculate the population mean, you can calculate population standard deviation. Right, so that's the easy part. And now this is the formula we need to spend time on a lot. So this is the formula to calculate probability using binomial distribution. So in this formula, probability of x equal to k equal to cnk p to the k's power times 1 minus p to n minus k's power. And where k can be anything in the sample space. So sample space of the binomial variable is from 0, 1, 2, 3 up to n. So think about the common sense. You have n observations to look at. Every observation can give you either success or fail. And what is maximum number of successes? Successes is s, right? X, right? So max number of successes will be n when every observation gives you success. And what's minimum number of successes? When every observation gives you fail, right? Then you don't have any success. X will equal to 0. And then when some of the observation give you success, some of the observation give you fail, then you could have, you know, other numbers between 0 and n. So the sample space is from 0, 1, 2, 3 up to n. Okay. So then basically the formula are able to calculate the probability of any single outcome in the sample space. So you can do any value of the sample space to plug in the calculation. N and P are the population, are the parameters of the binomial distribution. So they are provided already. And the K is the only number that's going to change for the same binomial distribution when you do the calculations. Okay. And then when you look at the formula now, we have power function, p to the k's power, and another power function, 1 minus p to the n minus k's power. Power function is very easy. So please get a calculator that has a power function. If not, you need to multiply it, you know, a few times. That's not as convenient, right? And the one that struggles some students is the front part, CNK, okay? So what does CNK means? CNK means a combination, okay? A combination. It's a number of ways to choose K item from N items. And combination can be calculated from another function, this called factorial function, okay? So factorial function, if you never learn about it, I'm gonna give you a little introduction here. It's very easy function and it's used a lot. So factorial functions defined as, you know, you have a number, any number, work with a factorial function here. Then n factorial will equal to from number n, start, and then multiply by, the next number is n minus 1, and then multiply with the next number is n minus 2, and then keep multiplying until it reaches 1. So basically, n factorial is a product of n numbers between n and 1 by the step of 1. So then if you think about the definition, if you have number 1 has a factorial for a function working on it, then 1 factorial will be 1 and it's a rated end, right? So 1 factorial equal to 1. And 2 factorial by that definition will be 2 times 1, and that's it, right? So that 2 factorial equal to 2. And then 3 factorial will equal to 3 times 2 times 1, right? From 3 down to 1. So that equal to 6, and so on, right? So 4 factorial will equal to what? 3 times 4 times 3 times 2 times 1, right? Equal to 24. So, and so on. So you can get a factorial function pretty easily. And other than that, there's a special factorial function. We have a number 0 can have a factorial function as well. But this is not coming from this definition. This is manually defined, right? So just need to remember, 0 factorial doesn't equal to 0. 0 factorial actually equal to 1. Okay. So then why do we create a factorial function? So I'm gonna spend a little time on factorial function. All right, so why do I create a factorial function? So in statistics, a lot of time we want to deal with, a number of sequences. So for example, if you have 3 items, maybe 3 students, or 3 tables, 3 chairs, 3 buildings, or 3 anything. So if we want to know how many different order can we have between the 3 items, we know ABC is already 1 order, right? So what other orders can we have? We could have A, C, and B, right? We could have B, A, and C, right? We could have B, C, and A. We could have C, A, and B. We could have C, B, and A. Are there anything else? No, that's all different kind of orders we could have, right? So when we list it, we can count there are 6 number of different orderings, right? But if we want to get that answer right away, very quickly, without listing those, basically that will be 3 factorials, which is 3 times 2 times 1, which is 6. So we can get it very quickly. For the small numbers, for example, when you have 3 items, it's not too bad to list. What if you have 10 items, right? What if you have 20 items? It will be impossible to list. It will take forever. But we can always just, with a factorial function, we can calculate it very quickly, right? Just times 10, 10 times 9, times 8, times 7, times 6, times 5, times 1, right? So this is why we create a factorial function. Right, so then combination, C and K. Why do we need a combination function? So combination function is very useful as well. Right, so when do I use combination function? So for example, if you have A, B, C, and D, there are 4 individuals, 4 students, 4 books, and 4 whatever. If you want to choose 2 out of the 4, how many different ways can you choose it? How many different outcomes can you get? In this case, order doesn't matter. When you choose A and B, it's the same as you choose B and A. Basically, those 2 items are being chosen, right? So then how many distinct outcome can you have if you choose 2 out of 4? So let's list it very quick. We could have A and B being chosen, right? Then you could have A and C being chosen. You could have A and D being chosen, right? So that's 3. And do we have more? Of course we do, right? We could choose B. B and A is the same as A and B, right? They're just chosen different order, but it's the same outcome being chosen. So we could have B and C. You could have B and D. And then you could have C and D, right? Okay, so then how many different ways can we choose? 1, 2, 3, 4, 5, and 6, right? So I have 6 different ways to choose. But if we want to get that number of different ways of chosen very quickly without listing it, it's easy to list that choosing 2 out of 4. But what if choosing 2 out of 10, right? It's not as easy anymore. What about choosing 3 out of 100, right? It's not as easy anymore. So we want to create a function, and that's where a combination function comes in. So we can calculate this number of ways to choose very quickly. So K will be how many items you want to choose, and N is how many items you're choosing from. So C and K. N is, in this case, 4, K equal to 2, right? So here we have C for 2. Okay, then we just go by the definition of the combination. So we just plug in numbers. N will equal to 4. And K will equal to 2. And K will equal to 2. And N equal to 4, right? So plug in the numbers and we can calculate. On top is 4 factorial. On bottom, it will be 2 factorial. And then 4 minus 2, it's still a 2, right? So then we can calculate. So in here, we can expand the factorial by definition. 4 factorial is 4 times 3 times 2 times 1. And 2 factorial is 2 times 1. But we have another 2 factorial, right? We have 2 factorials. So then it's a simple math, right? 4 times 3 times 2 divided by 2 and then divided by another 2, right? So on the bottom is 4. On the top is, you have cancel is 4. So you have 6. You can use your calculator to calculate that. So we have 6 different combinations, right? So combination is pretty easy to calculate if you understand how it works. So even if you calculate combination of C10, 3, so choose 3 out of 10, how many different ways are there to choose? So for example, if we set N equal to 10 and K equal to 3, how do we calculate this? I mean, if you want to list it, you have A, B, C, D, E, F, G, H, I, J, and then you choose 3, A, B, C, A, B, D, A, B, E, there are just too many, right? It's very hard to count. But we can calculate that very quickly. So we just go by the formula. And plug in numbers. N equal to 10, K equal to 3, N minus K, N is 10, K is 3. And then we calculate. So 10 factorial on top, we just keep it as is. We're gonna just get rid of this subtraction in the parentheses first. Parentheses has higher order operation than the factor function. So that's 7 factorial, right? And now we're going to calculate this. So some student has a factorial function on the calculator, but I still don't recommend you to use that function to calculate the factorials because it's not convenient. It's a lot easier to just expand the factorial function by definition. So 10 factorial is 10 times 8, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3. You don't have to list them all. You can just, list some of them, and as long as you know. But, here I'm demonstrated. I don't want people to get confused. Right. And then the bottom, 3 factorial, we're going to expand it by definition. 3 factorial is 3 times 2 times 1, right? About 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So when you look at this, then it's very clear that 1 through 7 on the bottom, 1 through 7 on the top, they are exactly the same, right? So for the fraction, they will cancel out. And then whatever is left is just, on top you have 3 numbers, on the bottom you have 3 numbers. And if you're good at canceling, you can keep canceling, right? 2 will cancel with 8. So you have 4 left. And 3 will cancel with 9. And you have 3 left. 3 times 3 equal to 9, right? And then everything else is done. And on the bottom, it all become 1. Everything's canceled out. On the top, you only have 3 numbers left. 3 times 4 times 10, right? 3 times 4 is 12. 12 times 10 is 120. So this combination will equal to 120. Right, so that's what a combination is. Now let's go back to the binomial formula. So if we know what the combination is, then for the 2 power function, we just multiply it together, and that's it. Then that will be the probability of x equal to k. Right? So I understand some students never learned factorial function in high school or or before. So I'm not going to require you guys to calculate this combinations, right? So instead, for every combination you need, it will be provided. So I'm going to tell you what is C10(1), what is C10(2), and so on. So you don't have to worry about calculating the combination. That will make the calculation a lot easier, right? And anyway, we are not really focusing on math that much in the statistics class, but we have to use math, right? Okay. So that will reduce a little bit calculation load. So this is a very simple example. If we know a variable x has a binomial distribution with parameters n and p given, can we find the population mean and population standard deviation of variable x? Just using the binomial formula. Population mean, n times p, population standard deviation, square root of np times 1 minus p. And plug in numbers n and p in there. You can calculate mu and the standard deviation, right? Mu and sigma. Right, so that's easy. Now let's look at the practice here. A student who take a quiz decided to randomly choose an answer for the single choice questions on a test. There are 10 single choice questions, and each question has 4 choices. Suppose the probability of each question being answered correctly are independent. And if you randomly choose answer, they are independent, right? One question being answered correctly or not is not going to affect the other questions, right? So then the variable x is defined as number of questions answered correctly. And it need to ask you, what's the distribution of x? We're learning binomial distributions. X must be binomial distribution here, but you need to understand why. We need to use the binomial setting to verify that, right? And what is the mean and standard deviation of x? So just like what I did here, right? If you know the n and p of the binomial variable, you can calculate population mean and population standard deviation. And then lastly, what is probability that student will get 70% or higher on the grade? All right, so now let's work on this. I want to save this calculation for a little bit later for that combination calculation. But if we, right, so variable X is number of questions being answered correctly. So this is a variable of interest. Then to determine the distribution of this variable, we need to understand, hey, this is a count variable, right? And if it's a count variable, it could potentially be a binomial variable. So we need to check with a binomial setting. Do we have fixed number of n observation? So when you count number of questions being answered correctly, how many questions are there that he's attempting, right? So we know there are 10 questions in there. And then are the n observations independent? Will one question being answered correctly or not affect the other question? You know, the problem tell us they are independent, right? But if you use common sense, they are independent as well. One doesn't affect the other. And then setting number 3, do every observation has 2 possible outcomes? For every observation is every question, right? For every question he attempts, are there 2 possible outcomes? It will be either being correct or incorrect, right? So then one of the outcomes is success, the other is failure. Correct and incorrect, which one's success? So that will be dependent on what is being counted, right? So we're counting number of questions answered correctly. So that means correctly will be success, right? And then lastly, do every observation has same probability to be success? So there are 10 questions. Do every question have the same chance to be answered correctly? So there are 4 choices and only one choice is being correct, right? So for every question, the probability being correctly will be a quarter, 25%, right? You choose 1 out of 4. If you choose randomly, there's 25% of chance to be correct, right? So then we verify the binomial setting. We can conclude the variable X does have binomial distribution where n equal to 10 from first setting and p equal to probability of success from the last setting, right? So X is binomial where n equal to 10 and p equal to 0.25. So that's the answer for the first part of the question. You need to give it the distribution and the distribution parameters. So in the work, you don't have to write the binomial settings out, but you need to go through that in your mind, right? I'm not gonna grade on those, so you don't have to write it out, but you need to go through those to identify if the variable is binomial or not. Okay, so that's part 1. Part 2, we need to find the population mean, the population standard deviation, right? So population mean is mu by the formula, mu will equal to n times p, right? So this is easy calculation, 10 times 0.25. So that will be 2.5. So that means, you know, if many students are doing this, they go to the test with 10 questions. The average number of questions being answered correctly will be 2.5, right? 2.5 questions. And then population standard deviation will be sigma. And sigma equal to square root of n times p times 1 minus p. I'm going to copy the formula from here, so I don't have to type it in Word, which is kind of time consuming. So then we just plug in numbers again, right? N is 10 multiplied by P. P is 0.25. And 1 minus P. P is 0.25. You know, you can, if you're quick, you can just write 0.75 for the parentheses part, right? So then this is an easy calculation. You guys can do it on a calculator. I'm gonna do it here very quick. Square root of 10 times 0.25 times 0.75. So that'd be 1.37. Okay, so part 2 is done. What's the population mean? What's population standard deviation? And next question. This is what you know is new, and this is what I really want you guys to know how to find. How do I find the probability? So what's the probability the students will get 70% or higher? So for this, we need to find a probability, and then we need to really figure out how to write the event regarding to the questions in terms of the variable x, right? So 70% or higher, what does it mean? If we use x out of 10 questions, how many questions does he have to answer correctly in order to get 70%? 7, right? So it need to be at least 7. At least 7. What sign do we use here? Greater than or equal to, right? Okay. So here, there's another thing we need to realize. What possible values can x be? What is the sample space of x? So this go back to chapter 10, right? Sample space. And in binomial distribution, we just talked about sample space. Sample space for binomial variable is 0, 1, 2, 3, 4, 5, up to n, right? N equal to 10. So greater than or equal to 7, what possible values can x take? Greater than or equal to 7, right? 7, 8, 9, or 10, right? So this will be x equal to 7, or x equal to 8, or x equal to 9, or x equal to 10, right? So then you can realize we have or connecting different events, right? So if we have or, what probability rule do we need to use? This is from chapter 10. This is addition rule, right? So then we can have probability of A plus probability of B, right? And then for the others, probability of C, right? Okay, so from here, then we can use the binomial distribution to do the calculations. Binomial distribution can only calculate the probability of one outcome at a time. It cannot find the probability of this event at one time. It has to find a single outcome, one outcome at a time, right? So I'm gonna use one example to find probability for one of the outcome, but for any other outcome, it's pretty much the same deal. So for example, I'm gonna find probability of x equal to 7. Okay, so then we need to use the binomial formula. We just talked about the binomial formula to calculate the probability, right? So this is the binomial formula. Equal to CNK times p to the k's power times 1 minus p to n minus k's power. So in the beginning, I always recommend you to write the parameters out. What is n? What is p? So these are from the distribution, right? We're dealing with this distribution, right? And what is k? K will equal to, when you look at the formula, K is right here, right? So then that means K is 7. And then the rest will be just plug-in numbers. So C and K will be C10, 7. And P, 0.25. K, 7. 1 minus P, 1 minus 0.25. N minus K, 10 minus K equal to 7. So please, every time when you do binomial calculations, give me this first. And then you don't have to give me in the middle steps. You can just give me the calculate the results after. But I want to see how you plug in the numbers correctly. The rest is just algebra, right? So then we're going to continue. I'm going to work on steps. So C10-7, that's a combination. You can calculate a combination like what we did earlier, right? Like this. But it's not required. You don't have to. For any problem that need binomial formula to calculate, the combinations are always provided to you. Okay, so you just need to look for the correct combination to use in here. Right? So we needed C10-7. C10-7 is right here. 120, right? So just gonna plug in 120 for that combination. And then we copy the rest down, 0.25 to the 7th power. And then 1 minus 0.25 is 0.75. And then 10 minus 7 as a power will equal to 3, right? And then, this is an easy calculation after here, right? So if you calculate this, I'm going to do it very quick here. 120 times 0.25 to the 7th power times 0.75 to the 3rd power. So it's 0.00309. If we keep 4 decimals, 0.0031. Okay, so this is probability of x equal to 7, right? And then same deal, you can calculate the probability of x equal to 8, I'm going to do this real quick. Okay, so I'm going to change the numbers. This is 8. Then NP will be the same, but K now will change to 8, right? So in the beginning, I would recommend you to list NPK all the time before you plug in, just in case you make a mistake. So N is 10, K is 8. And P is 0.25, it doesn't change. K is 8 here. And P doesn't change, but K will change to 8, right? So then here you need to modify C10-8. What's C10-8? C10-8 equal to 45, right? So I just need to borrow it over there. So the first number is 45 as the combination. And then 0.25 to the 8th power, right? We need to change that to 8. And then 0.75, we know on the power is 10 minus 8, is 2, right? So then we can calculate this. So equal to 45 times 0.25 to the 8th power times 0.75 to the square, to the 2nd power. It's 0.0004 if you keep 4 decimals. Okay, and so on, right? You can find the probability of x equal to 9. You can find the probability of x equal to 10, and you add it up. That will be the probability of getting 70% or higher, right? So, here I give you all the calculations for the entire sample space. By the way, you really don't need all of them. We only needed 7, 8, 9, and 10, right? So 0.0031, we calculate that. 0.0004, we calculate that. And 9 and 10, they're very, very small, basically. And probability is 0.0035. So, based on this probability, well, you want to go to a test without preparing for it? How likely are you going to pass the class? Not very likely, right? So please do study if you want to pass any class. If you just want to try your luck, the chance of success is very low. Don't do that. Be prepared. Okay. Right here, so here's a second animal for the attendance check. This is a very cute squirrel, right? Right, so here's another practice. And if you like gambling, maybe you're interested in this game, and maybe this will change some people's opinion when it comes when they go to casinos, right? So we're gonna talk about the design of a casino game, a roulette wheel. So if you have never played a roulette wheel game, it basically is a wheel, has 38 slots, numbered from 0 and 00, and then 1, 2, 3, 4, up to 36. So there are 38 slots with numbers. And each number has a color. So the slot 0 and the 00 has green color, and 18 other numbers are red, and 18 other numbers are black. So total of 38 numbers. The dealer will spin the wheel and then drop a ball at the same time. So the ball will keep rolling in the wheel, eventually will land on one of the slots, and that will be the winning slots, right? So the gambler can bet on different things. They can bet by color, they can bet on number, they can bet on combination of numbers. So, a lot of different betting scenarios. But we are just going to talk about a simple scenario. So we're talking about betting on red. Right? So if you bet on red, you only win if the ball lands on any red number. As long as it lands on red number, then you're going to win. Now, what's the probability of winning with a bet on red in a single play of the game? So you just play one time. How likely are you going to win? Some people already figured out, right? So probability of winning basically just probability of red, right? So how many reds do we have? 18. How many slots do we have? 38, right? So that'll be, if we calculate it, you can keep it as fractions as well, but later on, when we need to calculate probabilities, fractions are not as friendly as decimals. So we can convert it to decimals. It will be 4.47. So you have 47% of chance to win if you bet one time, right? That's not too bad. All right, so here, second scenario. If you decide to play the roulette wheel 6 games, and every game you're betting on red, what's the distribution of the variable x as the number of times the player wins? Right? So the variable is a counting variable, right? So it could have binomial distribution. So let's work on this. So x is number of games the player wins out of 6 games he played, right? Then this is a count variable. It could potentially be a binomial variable, but is it binomial or is it not? We need to check the binomial setting. First setting, do we have fixed number of n observations? So when you're counting number of games the player wins, do we know how many games he played, right? So we do know that's equal to 6 games. In the second setting, are n observations independent? So n observations basically is the 6 games here, right? We are will the first game he played, he wins or not, affect the second game he plays? It doesn't. Every time it's a random number to win, right? So they are independent. And third setting, do every observation has two possible outcomes? For every game he plays, does it have two possible outcomes? Of course, he could either win or he lose, right? So which one's success? Win is success. Why is a win success? It's not because he wins money, right? Win is success because we're counting the winnings, right? If the variable is defined as number of games the player loses, then lose will be success. So win or the success or fail is basically just looking at what outcome is being counted. It's not really about succeed or fail in real life, right? So win is success. It's only because we're counting wins, okay? And the last setting, do we have same probability for each observation to be success? So basically, it's for winning, right? And he's betting on red. What's probability of winning on a single game, right? For every observation. And do they have the same probability? It is. It's always 18 out of 38, right? So it's 4.47, right? So then we can decide the variable does have a binomial distribution. And parameter n from first setting, parameter p from the fourth setting, right? Again, you don't have to write the four settings out, but you need to go through that in your head to determine the variable has a binomial distribution. Okay, so that will be, part B, right? So now let's look at part C. If you bet on the same amount on each play, and if you win exactly 3 times out of 6 plays, you will break even, right? What's probability that you will break even? So we need to look for probability of break even. And we mentioned the only way you can break even is you win exactly 3 times, right? Which indicate how many times you lose. 3 times as well, right? You play 6 times. If you win 3 times, you lose 3 times. So we can calculate this very quickly using the binomial formula we learned, right? So if we copy the binomial formula, so then before you calculate, I would recommend you in the beginning, write N, P, and K's out. N and P come from the binomial distribution you just figured out from the binomial setting. And K will equal to whatever the value you're calculating for, right? So K equal to 3. And then we can calculate. We can plug in numbers N, P, and K into the calculation, right? So N equal to 6, K equal to 3, P equal to 0.47, K equal to 3, P equal to 0.47, N equal to 6, K equal to 3, right? And then calculate C63 as given, right? C63 is 20. So that'll be 20 for the combination number, and then 0.47 to the cube. Then 1 minus 0.47 is 0.53. And 6 minus 3, the power is 3 as well, right? And then, you know, you don't have to show steps here. You know, this is just algebra. You can plug into the calculator real quick. So that's 20 times 0.47 cubes, then times 0.53 and cubes. So the answer is 0.309. So about 30.9% of break even. Right. So then for the next part, if you win on fewer than 3 out of 6 plays, you will lose money, right? So even when you win 3 times, you're gonna break even. If you win less than 3 times, you're gonna lose, right? So what's the probability of losing money? That will be probability of x is smaller than 3, right? And binomial distribution cannot calculate a probability with an event with a smaller than sign, right? So you have to change it to be equal to. So now you need to think about the business of sample space, right? So what values can variable x have? The sample space for binomial variable is always from 0 to n, right? So 0, 1, 2, 3, 4, 5, and 6. So smaller than 3, we need to be either 0 or 1 or 2, right? So that'll be probability of x equal to 0 or x equal to 1 or x equal to 2. And now probability rules, right? When you have or connecting, we can use addition rule. So it'll be probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2, addition rule. And then for each of the probability, you can use the binomial distribution, right? Exactly like this. And then p will stay the same, but the k will change, right? K will be 0, will be 1, will be 2 in the 3 calculations here. And you can calculate, right? We're not going to go through that. But, we've done quite a few examples on that. But if you have questions, please let me know. And the last portion, if you win on more than 3 out of the 6 plays, you will eventually lose some, you will eventually win some money, right? So out of the 6 games, what's the probability of winning money? So that'll be probability of x greater than 3, right? And greater than 3, of course, if you look at the sample space, will be either 4, 5, or 6, right? And then, of course, you can use addition rules as well. So probability of x equal to 4 plus probability of x equal to 5 plus probability of x equal to 6. And for each of the probability, you can calculate using the binomial formula, just like what we did here. Right? So if you go through all the calculations, you're going to find out that probability of losing money will be 0.0213 plus 0.1148 plus 0.2582 will be 39%. And probability of winning money will be 0.2092, 0.0753, and 0.0113, and that's 0.2958. So it's about 30%. So if you play 6 games total in a casino for roulette wheel, the chance of you break even is 31%. The chance of lose some money is 39%. The chance of winning some money is about 30%. So what can we conclude? The casino is more in favor of the casinos, the dealers, right? They have about 10% of chance, 10 more percent of chance to win your money, right? Okay. So all the casino games has a lot of statistic, design behind it so that they can get the benefits of it. I don't recommend you to really try to win some money when you go to casino. You can try to have some fun, but don't expect to win, too much money, right? It's not gonna work. Another thing is, if you really want to win some money, you need to know when to stop. You need a luck. the longer you stay in the casino, the closer the probability will be to the theoretical value. So if you stay overnight, it's almost guaranteed you're gonna lose money. If you really wanna make some money, win some money, when you win, stop, okay? So binomial distribution is very, very useful. It's used a lot in quality control. So, you know, when you are a manufacturer, you produce a lot of products, but you want to make sure the fault rate is under control, right? So, for example, if you produce like 20,000 of CDs, and you want to check if the CD is, you know, the fault rate is controlled. So you need to check the CD, but you're not able to check those 20,000 CDs. This can take forever, right? So you can randomly select some CDs. For example, you can randomly select 100 CDs, and then you're gonna check carefully for those 100 CD if they're good or not, and then you're gonna define a variable X as number of defective CDs out of the 100 CDs being checked. Then, you know, the variable X will have a binomial variable if you go through the binomial setting. And then you can find, you know, some probability related numbers to tell you if your, you know, quality is good. So binomial distribution. In the homework, there's a question about pistons. You're trying to see if the pistons is, you know, good or bad. So, but be careful. The success doesn't necessarily mean it's a good thing, right? The success outcome is always just the outcome being counted, right? So how is a variable defined? That defines the success for you. Okay, so this is a little summary. So the key thing is, you know, keep in mind sample space is from 0 to n for any binomial variable, and is a parameter of the binomial distribution. And the binomial distribution is discrete, right? It can only be the fixed number 0, 1, 2, right? It cannot be 0 0.1, 0 0.2, 0 0.3, right? So continuous discrete, that's something we talked about in the first chapter, so that they're important concepts. And then be able to use the binomial formula. The only trouble that you may have is the combination part, but you know, I try to reduce the calculation effort. I gave you the combination number for every question that you may need it for the binomial calculation. And the power function, everyone should be able to handle it with the help of your calculator, right? So it shouldn't be a too big an issue. And then binomial formula also has a population mean and population standard deviation calculation. They're not quite useful now, but we're going to talk about a process after we cover normal distribution. So when we use normal distribution to approximate binomial distribution, normal distribution has parameter of mu and sigma. So you need to borrow those mu and sigma from the calculation here to do the process. So it's too early to talk too much about it, but just keep in mind, we need to calculate mu and sigma for some processes for binomial distribution. All right, so then this is it. Send me questions if you have any, right? Thank you.